Oh my gosh.
Alright, well, welcome to the next homework video. We're going to be dealing with this assignment, page 58, numbers 35 through 46. Let's go. Number 35 asks us, draw complete graphs with 4, 5, and 6 vertices. How many edges do these graphs have? Can you generalize to n vertices? Well, first of all, let's draw them. Most students orient 4 vertices like this. To be complete, every vertex has to connect to every other vertex. So you get things like that. Once they've drawn them for a while, most students start drawing them like this because it's easier to see all of the connections oriented in this way rather than that way. They're equivalent, but easier to look at. Then 5 vertices connect to everything else. And then 6 vertices connect 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3. 1, 2, and 1. So, with 4 vertices, we have 6 edges. With 5 vertices, here's the way I think of it. I had to connect to 4 places, 3 places, 2 places, and 1 place. So, it's going to be, with 5 vertices, you start at 4 plus 3 plus 2 plus 1. 4 plus 3 plus 2 plus 1. So 4, 7, 8, 9, 10 edges. Then following the same pattern with 6 vertices, I would have 5 plus 4 plus 3 plus 2 plus 1. It ends up being 15 edges. So if I want to generalize to n vertices, I'm going to start with n minus 1 plus n minus 2 plus, and I'm going to keep going until I hit 2 plus 1. Wow, this pen is failing. So that would be one way to write this formula. There are easier ways to write this formula, but I'm not going to think about or cover them. So this is the type of thing I was looking for. If you had something like that, nice. Good. How many traveling salesman problem tours would these graphs have? So, up here, how many tours would we have? Well, we'd start at one of any of 4 vertices. From there, we would have 3 places we could go. From there, we would have 2 places left. And from there, only 1 place left to go. So, that would be 4, 12, 24 places. But you can see where it comes from. Here, there's 5 places I could start. Times 4, times 3, times 2, times 1 is 5 factorial, which turns out to be 120 different ways you could do it. This is really the issue we run into with computing power. 5 vertices is not very many to have 120 possibilities that we have to explore. With 6 vertices, then, is 6 factorial, which is 6 times 5 factorial. 6 times 120 is 720 different paths that we would have to, that we'd be interested in looking at to know what is the optimal way to go around that tour. Problem 36. I wonder why I scratched it out here. Problem 36. Calculate the values of all of those. You could just put those in a calculator. The big thing I want you to see is these things blow up massively fast. 10 factorial is a huge number. I know it's well into the millions. I don't know exactly how much. 27 factorial. 27 is not a very high number. 27 factorial is more than the number of particles in the known universe. It's a vast number. Okay. Then find the number of traveling salesman tours in the complete graph with 9 vertices. Well, you can see the total number of traveling salesman tours when you have 5 vertices is 5 factorial. So with 9 vertices, it's going to be 9 factorial. Problem 37. The following table shows mileage between 4 cities: Springfield, Urbana, Effingham, and Indianapolis, Indiana. So here is our distances between them. A, we want to represent it by drawing a weighted graph complete on 4 vertices. So here's our graph on 4 vertices, and I've already labeled them for the cities. And there we've made it complete, because you could drive from any city to any other city. Weights, I have to add in the distances between them. From E to I is a 147, so 147. From E to S is 92. from E to U is 79 miles. From I to S is 190. From I to U is 119. And lastly, from S to U is 88. So, there we have the complete graph with the weights on it. That's what you needed in part A. Part B, use the weighted graph to find the cost of the 3 different Hamiltonian circuits in the graph. So, 3 different Hamiltonian circuits. If I'm going to start at U, I have U, I, E, S, U would be one of them. Another tour starting at U, I gotta think, U, I, E, S, U, I left out the bottom edge. So, U, S, I, E, U, U, S, I, E, U, S, I, E, U leaves out this edge, so now I need to leave out this edge over here. So U, I, S, E, U, U, I, S, E, U, and the weights of them, U, I, E, S, U, U, I, E, S, U would be 119 plus 147 plus 92 plus 88. USIEU is 88, 190, 147, and 79. 88, 190, 147, 79. And UISEU is 119, 190, 92, 79. 190, 92, 79. So those are the 3 possible paths we could take around this. I don't have a calculator with me, and I don't think it's useful anyway. You would add these up to find out the total weights of them. For B. C, which circuit gives minimum cost? Again, if you had your calculator, you would just add these up and look at whichever one has the minimum cost. By inspection, it looks to me like it's probably this one. So that would be UIESU. And just if you were planning this road trip, this is the tour you would want to make to drive the least miles. Part D. Would there be any difference in parts B and C if we start at vertex I? Here's the idea. If this is, and I'm assuming that I'm right by inspection, I would have to add these up to know this is the optimal tour. If that's the optimal tour, UIESU, then if you're starting at I, the tour doesn't change. IESUI. Or IUSEI. It doesn't matter. Either direction you go, it doesn't matter where I start. I could start at E and do the same tour. Nothing changes. So, part D, would there be any different answers if we start at I? No. The answers would be the exact same. I apologize for some of the noise in the background. This is my wife is cooking as I'm doing this. So, part E, the question is, if one applies the nearest neighbor method starting at U, what circuit would be obtained? Well, if I'm going to start at U, nearest neighbor says first I would go to E because that's the least, 79. From E, I'm going to take the least, which is 92, so I'm going to go U, E, S. And then once I've done those two, I have no other choice because I have to visit I and get back to U. So I have to go up here and back there. So I get U, E, S, I, U. UESIU would be my tour. Good. 36. Wait, no, that's not right. Oh, I had moved 36 over there. Okay, 38. So, 38, I think should be on the camera there. It looks like it is. After a party at her house, Francine has agreed to drive Mary, Rachel, and Constance home. If the times between her friends' homes are shown below, which route gets her home the quickest? The only way to get actual answers on this is to do the brute force method, which is what we did back here. This is brute force. You list out all the possibilities. Hey! My dog was getting at the food. List out all the possibilities, add them all up, see which one is best. Looking here, we have to start at Francine's house in the middle. I'm definitely going to avoid the weightiest edge, which is 15. So when I think of the cheapest tour, I'm probably traveling around here. 7, 11, 10, 14. That is going to be the optimal tour. FRMCF. FRMCF. If I weren't worried about the length of these videos, I would write out all 3 tours. I would calculate the weight of all of them and pick the smallest. But I want these videos to be relatively short. So that's going to be your optimal tour. 38. Oh, whoops. That was placed in the wrong place. Wait. Oh, whoops. FRMCF. Not using this one at all. Sorry about that. 39. What route would Francine have to follow to get home as quickly as possible, assuming she promised to drive Mary home first? So if she has to drive Mary home first, I still would like to avoid this edge, but I think now I don't have the option, because I have to go either this way or this way, and either way I have to cross here to get to the other person's house. So I'd go up, I'd take 10, 15, and 7, because that's less than 11, 15, and 14. So Mary, Constance, Rachel, then Francine. If she promised to take Mary home first, it's going to be up there. Wait. 10, 15, 7. So 10, 15, 7 is going to be her best tour. 40. Francine is planning to live at her friend's home and then spend the night at Rachel's house. So she's going to start at her house and end at Rachel's house. So she has to get here and there in the least possible. It's going to be, because I still want to avoid this 15 edge, I'm going to take the 14, 10, and 11. Or my other option to end here would be 8, 10, 15. So 14, 24, 35, or 8, 18, 20, 33, which is better. So I'm going to go up, over, and then over there, which is here, down there, over there, starting at Francine's, ending at Rachel's. Problem 41.